Hello everyone, thanks for joining me here. This is Verde Arbusto, the Schumann Resonance Harmonics channel, and this is actually part 5 now, I think, or part 6. Alright, so in this riveting series, I'm talking about how we get the signal. I'm talking about the complicated pathway, just as this video series has been, on this topic of what it takes to get the actual signal, and we're doing maybe a little forensic work on looking at the dependencies. How do I say this? Oh, it's a love thing. We're looking at the dependencies, what are reported from Tomsk. Let's do a quick review. This is another video, quick review. All right, so so different points. We see they're at rest state at different points. So I've gone through this before, but this is just a reminder that the amplitude, the ball antenna, is the only one where the zeroing out state is how do I say this? Where the zero state, they're all equal, they're all even, they're at zero, basically. Whereas these other ones, the speedometer antenna, this is pegged way at, its at rest state is here, at 8, way up at the top, and then this is at the, not quite at the bottom, this one's somewhere in the middle, this one's somewhere in the middle, So the spectrograph is plotted based on these dependencies. And that is an important thing to remember, that that where you're getting the information from. All right, so that's just a point to bring up. Right. So also that the ball antenna is different from the magnetic induction coil. I have no. That's it. All right. So, again, this just reminder, quick reminder, that that's the ball antenna on top of the stick. This is just a diagram. It's not the actual. How do I say this? This is not the actual antenna itself. This is in construction. So that's what they're showing when they say schematic diagram. It's just a basic thing, because this is actually supposed to be at 90 degrees from these two. All right, so the antenna is supposed to be upright at 90 degrees from the base, and these are set 90 degrees from each other. All right, so that's just a basic reminder of the orientation that the antennas are supposed to be in. All right, so all right, so this is some basic information. Experimental measurements on Schumann resonance magnetic field components involved antenna implementations that are usually induction coils with efficient magnetic properties and enhanced detection sensitivity. Ferromagnetic core exhibits a relative magnetic permeability of the order of 10 to the 5th, providing high induced voltage amplitude. Mu metal is a soft ferromagnetic material that exhibits a maximum magnetic permeability of the order of 2 times 10 to the 5th. Our antenna implementation is based on induction coil architecture with mu metal core material. The mu metal material ASTM-A73 alloy 4 exhibits very small coercive force, very low core loss, and remanence due to the fact that our core is a rod that is open-ended. The resultant equivalent magnetic permeability is much smaller than the mu metal relative magnetic permeability is given up by equations 1 and 2, see below. Also, it strongly depends on the relative permeability of the core material, as well as on the induction coil geometry through demagnetization factor N. Equations 1 and 2 give demagnetization factor N, and the resultant magnetic permeability of the Greek letter there, I'm not sure what that is, micro, whatever, mu, I guess it's mu, of an induction coil. All right. Where M, in our equation, M, is the length of diameter core ratio, M equals 300 over 25 equals 12 in this research, and mu R is the relative magnetic permeability of the core material in this work, N equals 0.0151. In practice, choosing a quite large induction coil length is a benefit due to the resultant high magnetic permeability, 23, but taking into account that as the length of the induction coil increases, the ratio M also increases, eliminating the demagnetization factor value N as observed from equation 1. That yields to the fact that the resultant magnetic permeability, our variable here, exhibits quite strong dependence of relative magnetic permeability of the core material due to equation 2. Moreover, the value of mu R, our variable R, presents crucial instability resulting from temperature or applied field frequency variations. Therefore, the induction coil sensor performance may be crucially affected and degraded through variations of magnetic permeability. That means issues from the core. You're losing magnetic, it's bleeding from your, how do we put this? You're losing the magnetic charge from the permeability. All right, the core material. All right. More. Okay, it was there. As that material presents high relative magnetic permeability, equation 2 is unified to equation 3, and in the induction coil magnetic permeability depends on the value of demagnetization factor N. All right. So this is way more than I really want to get into relative to this, but. As far as equations, but I want to show you how the antennas are made. And this is what they're doing. All right, so it depicts a block diagram. Ay caramba. All right. So what this diagram is showing you is it's a block diagram of the single induction coil, and Table 1 summarizes the corresponding geometry values. The windings should be laid in the core of 70 to 90% of its total surface in order to take advantage of maximum possible flux. Flux U. All right, so this is a cross section of the wires. The wires are here. N turns, that means 1,000 million turns, okay. And the D core, okay, so the turns are showing you that could be there's a certain variable, depending on the size of the wave you're looking for, you would have various amount of turns in here, various thicknesses of wire. Okay, so this is a technical introduction to the heart of the quality detector of the Schumann resonances. Okay, this is your permeable, magnetically permeable material, and this is your windings, a gazillion windings, and then they have that all measured out there, and this height measured there, the total height of the core, and this is all by formula and all of this kind of good stuff. Okay. I'm introducing. There's way more technical stuff here than I want to go into at length. I'm introducing the induction coil. I'm giving a technical introduction to the induction coil and the physical. Before addressing what can be wrong at Tomsk, like I said, I've said all through this mini-series here that this is basically a precursor to knowing what exactly is wrong at Tomsk, at our favorite Schumann Resonance dispensary. It's really important that we know the data path. We know how we're getting the signal. So that's what I'm doing here is a long-winded answering of the question of what's wrong with the data at Tomsk. Is before we can answer that, you have to know generally how these things work. I really truly feel this is what my guides have told me, and this is where we're at in learning about this, learning about the Schumann resonances at this time is learning how to get the signal, because we're not getting anything useful at this point unless you're diagnosing the problem. I am a technician, I'm a field technician, have been, and so let's look at the schematics of how this thing works. So that's what this here mini-series is about, diagnosing basically the wonky data from Tomsk. All right. So we have our diagram, and I'm going to give, again, another one I'll give the reference to. You see the diagram of the windings. All right. So now I don't want to talk about more. Oh, except they're giving you this. All right. So I'll read this really quick. Single induction coil geometry. Our induction coil architecture is depicted in such block diagram. The core mu metal material length, I core, and with diagram, D core, as well as the length of the wire windings, I windings, are also shown. We implement that induction coil antenna using copper wire, diameter D, and making N turns of windings that cover 79% of the total core length. The total induction coil diameter is defined by the thickness of windings, T, and the core diameter, D core, provided that the total number of turns should approximate to 40,000. All right, so he's saying there are 40,000 windings on this bad Larry Jackson here. Okay, that's how you develop the height. Right. So I'm going to scoot forward here and show you the Holy Grail. All right. So this says, Schumann Induction Antenna. Our magnetic field antenna consists of two identical back-to-back induction coils with mu metal core material. In order to achieve core alignment and excellent connection between the two induction coils, we used a clamp of mu metal sheets. Our antenna output terminals are connected to the pre-amplifier inputs. A plexiglass box is also used to protect the antenna and pre-amplifier stage mainly from moisture and humidity, providing also portability and stability. Through 3 SMA connections, the pre-amplifier output as well as its positive and negative power supply is accessible. So that's what these are, little access ports. All right, so signal conditioning chain. Okay, we get to basically the meat and potatoes of the operation here. They're showing you what it takes to finally, we get to the Holy Grail. After 5 long videos, or 4 or whatever, maybe it's been 100, I don't know. we get to the basic amplifier chain. What it's showing us are the caramba. Oh, why don't I let you see it yourself? All right, I'm back. I throw in the music because a lot of the stuff is so dry, and it's just, oh my God, my head is hurting. It could be from the Schumann, it just could be from, I'm just reading for over an hour now. 2 hours, 2.5, I don't know. It was daylight when I started, now it's nighttime. And I have taken the circuitous route on this. It's partially my own fault. Partially I haven't had enough caffeine. So thank y'all for being here. The music helps break things up. And if you don't like house and any or club or any of that, I feel sorry for you. But I need the music to kind of keep things going. All right. So where we're at with this in the amplifier chain, we're through this rather long article here from Springer Open. All right. So we have the induction sensor coil, then we have the preamp, then we have the filtering stage. You see the 1, 2, 3, 4. There's 4 filters there. Then the variable gain amplifier, and then the DAC unit. So there's from where you get it. You saw the antenna that's there, and then the preamplifier that's 1. All right. So they're numbered 1, 2, 3, 4, 5, 6. All right. So this is what our concern is. All right. So filtering and amplification chain. The architecture of our Schumann resonance detection and measuring system is shown in the schematic diagram. 2 amplifying stages, preamplifier, and 4 active filtering stages are the signal conditioning setup that provides signal strength and enhancement and bandwidth limitation in order to achieve Schumann resonance detection and measuring. The output of the last amplifying and filtering stage is connected to data acquisition system, DAQ. That system exploits data signal techniques and methods, providing signal spectrum estimation and measuring. All right, well, they didn't put a paragraph there, but I think that's... all right. All right, so we saw where... All right, so for better noise performance and less signal degradation and distortion, the preamplifier was mounted directly on the coil inside the plexiglass container as shown in Figure 2. All right. So I think we have already heard that or seen that. But there's a little tiny... The preamplifier is not a big thing. It's just taking that signal and, amplifying it, just the raw signal, that preamplifier. All right, so in there, this is the induction coil unit. So in there, it's in there. So it's maximum magnification here. So these 3 connectors right there go to this. Behind it is the little tiny thing is the preamplifier. So that gets it. If you're familiar with like home electronics or any of that, you'll know what, like an amplifier, like you can't plug a CD, you don't plug your speakers right into a CD player. Now it's different. I don't know. I mean, I don't know what's available now. But back in the day, there used to be a phonograph that needed a particular type of amplifier. And the receivers now don't have it, but in the back of amplifiers, you need to have the preamp stage to get it from a very small voltage up to a line level signal. And this, I don't know, I can't make that any more clear or basic. You just have to know some basic electronics here of what a preamplifier does. I mean, this is explaining a little bit more. I don't want to get into too much depth with this. Okay. Because this is just an introduction. It's long enough as it is, but I'm trying to give a good introduction to what is, what's happening with the Schumann antennas. All right, so by way of this diagram from these gentlemen from Greece. All right, so preamplifier. The first stage of the signal conditioning setup, which is a preamplifier, is shown in Signal 4. I showed you that the preamplifier stage is based on a non-inverted operational amplifier topology. The RC circuits at both voltage CC and voltage EE were used for decoupling purposes at both positive and negative supply voltages. Regular RC decoupling circuits were used in every stage of our filtering and amplification chain. The preamplifier's gain was equal to 3.55, and at negative 3 decibel cutoff frequency due to the RC filter in the output is 0.024 Hertz. In order to achieve additional low noise performance, the OPA 209 operational IC amplifier was chosen because it exhibits very good low noise performance. For further investigation, we designed and implemented 2 more preamplifier stages that are based on inverted operational amplifier architecture and instrumentation amplifier topology, respectively. Taking into account our antenna coil architecture, we provided both simulated and measured results. These results indicated that both of the 2 alternate preamplifier stages had limited performance. Okay, we're building us an antenna and a preamplifier. Preamplifier. She took my clothes, she took my hat, she took my amplifier. It's right here, baby. You got your amplifier right here. All right. So, you see a bunch of signals here. There's a ground, there's a resistor there. That's our input from the coil, VEE. I don't know what that is. That's resistor, the ground. All right. So, voltage on the. I'm not sure. It told us in there. I'm not sure what the VE is, but these are 2 different. This right here is made up. This voltage VCC is made up of this little guy here, and this VE is made up of this guy here. This is our little preamp unit, okay? And then it goes to, there's a negative, gets, the positive signal, oh good golly, the positive signal gets conditioned and the negative kind of hooks in there. I'm not even going to go and explain it more. I don't know that much about schematics. I think there are people who are more qualified to tell how that works. Okay. But they tell you basically here, the preamplifier. The first stage of our amplifying and filtering stage is based on non-inverted operational amplifier topology. The main goal is to provide low noise amplification on the extra low level induced voltage at the induction coil terminals. Resistors R7 and R3 through feedback connection define the gain value, as well as the output RC signal stage R2, C3 eliminates flicker noise for better performance. We also use bypass capacitors at both positive and negative power supplies. The capacitor holds a charge, among other things. The variable gain amplifier is the last stage of our amplifying and filtering chain. That stage is also based on non-inverted operational and amplifier topology, having a potentiometer in feedback instead of a fixed resistor value component. That potentiometer offers an efficient way to adjust total gain. All right, so we'll just, I'm not going to click on the full size image. Okay, so we're running through some of the basics. I'm at 25 minutes here, and I want to just give a run through on some of the graphs. All right, so this is our amplifier. These are a stack of batteries that are kind of powering this. All right, so this, no, that's our stack of batteries there, and that's our can with the amplifier in it, okay? It's part of the signal conditioning chain. It says metallic box or electromagnetic protection battery powered. B, experimental preamplifier voltage input noise. That's what this is telling you, the input noise. 20 microvolts per division. All right, so each one of these divisions is, I guess, here to here is 20 microvolts. If I'm reading that correctly, each division is 20 microvolts. All right. For electromagnetic shielding, we used a metallic box that accommodates the under test preamplifier stage and the necessary amplifying and filtering stage for noise investigation. Also, we used batteries for power supply of the total circuitry. The SMA output provides noise measurements using digital oscilloscope in order to achieve efficient estimation on equivalent input noise. The preamplifier inputs are shortened and the power supply is provided, measuring the total output noise at several sequential snapshots. We made observations that confirmed datasheet noise parameter value. Okay, a lot of word salad there. Okay. All right, so I'm not getting, I'm not getting into the specifics of this. It may or may not to you seem like I am, but I'm introducing the fact, just the most basic stuff here. The amplifier, the preamp, the amplifier we showed on the can. The preamp is on the antenna itself, the magnetic antenna. The preamp is in the amplifier is in the can. So now we're talking about the filtering stage. All right, I'm at 28 minutes. Filtering stage. Our amplification and filtering chain has second to fourth stages that are based on a Salin key filter and filter and twin T-notch filter architectures. The Salin key filter topology is a populated architecture mainly due to the fact that the filter performance exhibits very limited dependence on the operational amplifier performance. Also, the ratio of the largest passive component value to the smallest passive component value is very low. This is an important benefit in implementation. The twin T-notch filter architecture offers versatile and efficient methods to design and implement band stop filters using commercial operational amplifiers and standard values of passive components, which are resistors and capacitors. Moreover, using a resistor potentiometer at feedback line may provide adjustments that affect both the bandwidth and the resonance depth. The bandwidth and the resonance depth. Okay. In particular, the second stage of our amplifying and filter chain consists of a second order silent key low pass filter and a 50 hertz twin T-notch filter in cascading connection, figure 6. The bandpass gain of this stage is adjusted to 3.5 and the negative 3 decibel cutoff frequency is 46 hertz. The signal attenuation at 50 hertz is 10 decibels. So I'm not going to read more about that. You can go there and read the article yourself. There's a lot to this, and I'm trying to breeze my way through it. And I think I'm going to have to make another video, whether I like it or not, because I haven't gotten to the end of this. And like I said, I like this particular article because it's full of information that's very useful to someone when we talk about the antennas. I want to have a video that I can point to that tells people this is how the antennas work. And that's kind of what we're doing here. So, actually, I think what I'm going to do, I'm at the 31-minute mark. I think I'm just going to music out and just pick up. I think I'm just going to pick up where I think I said earlier, I got a headache. I've been reading for a while. So I think what I'm going to do is just maestro out of here, and I will pick up this the next video right where I left off here. And so, all right, so that's what my guides are telling me. Just take a rest, and I will come back and start posting these. All right, so thank you all for being here. This is Radio Busto, and I appreciate you being here, learning more about the Schumann resonances. This has been a kind of grueling, long video series, but maybe more for me than you. I don't know. But at any rate, thank you all for being here, and I will see you or talk to you in the next video. So thank you all for being here.